Hi, this is Dr. S.P. Arsa from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration control, we are discussing about the vibration generation mechanism. And in our previous lecture, we discussed about that how we can classify the source through which the excitations are being happen in the machine. And we discussed mainly about the unbalanced rotor, because this is a very common cause of vibration. We also discussed about the misalignment, and we know that the unbalanced which is being there in the rotor is also due to various reasons. We discussed about the resonant conditions, and we discussed about the various other features of the system's characteristics through which the excitations are coming in that. And we also discussed about the band or the board shaft, and when it is being excited, how the vibration spectrum is being coming out. And then if you want to analyze the vibration spectrum, say in the time domain or the frequency domain, we can immediately find out that there are more than one exciting frequencies are there, and even in the frequency response function FRF, we can simply see that there are dedicated exciting frequencies according to the defects, like in the bearings or in the gears or in the shaft. And even in the shaft, you see here the misalignment, unbalance. So we can analyze various features through the vibration signature, and we could easily figure out the source. So that's why we noted down in the previous lectures the various causes of the vibrations are. And then we discussed about that when these vibrations are there in the in this mechanism features, then how do we analyze these vibrations using the signatures? And then once you find out those things, then what are the possible other classification when these two or more defects are being interacted. So in the current lecture now, we are going to discuss again the vibration generation mechanism under the self-excitation, because we know that even the system is of the robust design, there is no defect, there is no unbalance, there is no deterioration or the wear and tear is there of the component through which the excitations are coming. Even the machine is inducing the vibration. The machine is always creating some kind of noise, and this is mainly coming under the self-excitation or the self-excited vibrations. So the system which is under the self-excited vibrations begin to vibrate of their own accord spontaneously, and the amplitude of these vibrations increases until some of the nonlinear effect limit is further increases. So that means we can say that when a realistic system is in the rotating feature, the nonlinearity is there. The nonlinearity in the system may be of various reasons. The geometric nonlinearities, we are considering, say at the contact region, the point contact, line contact or the surface contact, the deformation which simply coming in the restoring forces as a linear. But the real nature of the deformation with the force distribution or the mass distribution all along the component is nonlinear. This thing is coming under the nonlinear. Second feature in the nonlinear effect is having the damping nonlinearity, because the material which we always assuming the homogeneous material, but under the real situation the things are not the same. And even under the elastohydrodynamic lubrication with the viscous damping, we cannot say that at the entire load zone the film thickness of the elastohydrodynamic lubrication will remain same with the deformation, and even the mass distribution of the component. With these three we can say that there is a clear nonlinearity. And the boundary conditions, when the system starts, we know that the transient conditions are there, And because of these boundary conditions, say because of any eccentric loading or something you see here, we have always the nonlinearity. So the energy supplying by these you see vibration can be easily obtained from the uniform source of power which is associated with the system. There is no external excitation, it is only within the system itself. Because you see, due to some mechanism which are being inherent in the system, gives always rise some kind of the oscillating forces, and this force acting on the vibrating object is usually you see like external and independent of the motion. Then we can say that you see here the energy supplying towards the system side is inducing the vibration, and it has you see a single kind of power generation which is associated with the system only. But there are systems in which you see the exciting force is a function of motion variables like the inertia force, restoring force or damping force, and the elements are displacement, velocity and acceleration. And when these variables are varies with the motion with their like coupled part or these things, they produces the kind of excitations. And even the friction induced vibration, sometimes you see like when we know that the vehicle clutches or the brakes or any kind of you see the vehicle bridge interaction or the vehicle surface interaction, or even the flow induced vibration like you see like any kind of the fluid conveying pipelines, they are the perfect examples of the self excited vibrations like the CDs, DVDs motion, the machining part, the circular wood saws, all these are perfectly we can say a representation of the self excited vibrations. So self excited vibrations can represent an important phenomena, especially in the mechanical system with their own physical interpretations. And there exists a clear different source of self excitation which needs to be clearly understood with the using of mathematical modeling, which can immediately couple the inherent property of all the we can say object along with the other properties through which the self excitations are being inducing. So in most of the cases of the self excited vibration, it always represents a danger for safe run of different systems and the device, and therefore it is necessary to use the means of vibration suppression or at least to reduce the vibration intensity when there is no fault or there is no external excitations are being there. And the occurrence of this self excited vibration in any physical system is intimately associated with the stability of equilibrium positions as well. And if the system is distributed from the position of equilibrium forces which generally appear, and they are causing the system to move either from the we can say equilibrium position or towards you see the outside or away from the equilibrium positions. So we need to check it out that what exactly the occurrence of these self excited vibrations are in any physical system. And there are various systems where excitations are coming from the inside only due to its own displacement or inherent nature. And when a system is disturbed, the free vibration under these certain conditions can cause the excitations which makes the system further vibrate and can damage up to the extreme level. And an increase in vibration can cause further increase in excitation, and therefore we can say that the system can run out of the control with their amplitude. And when these system vibration amplitudes are higher, the restoring forces goes on increasing and increasing because of the inherent nature. And these increased restoring forces are absolutely like fighting with the other increasing amplitudes until a balanced feature is not being added to reduce the excitation of vibrations. And then we can say that by putting those control features, we can brought down the vibrations towards the limit cycle vibrations. and the excitation gets removed when the amplitude of vibration becomes 0, or else we can say that we can simply brought the system towards the equilibrium side. And once the system is just vibrating and that vibration initiated, the excitation comes into the effect and the system runs off with the increasing amount of amplitude until the limit cycle is not being reached. So, when such kind of you see the vibrations are being happening, we can brought these kind of vibrations under the self-excited vibrations. And the functions of many machine and devices such as the power picks, the drilling sets, or any compacting like the equipment like the hammers or anything, they are always based on the self-excited vibration, and these are being produced by the action of compressed air. And such machine can hardly be expected to operate efficiently without having a thorough understanding of the problems which are being existed and the stability of any periodic motions within the system. And since we know that there are periodic inputs within the system, but because of the system nonlinearity, the output is somewhat different what we are desiring. It may be periodic, it may be quasi-periodic, it may be harmonic, sub or super harmonic, or sometimes you see because of the nonlinearity of the system, it may be the chaotic one. So, these self-excited vibration can cause even the chaotic vibration which has the irregular features towards that. And then it is very difficult to brought down the entire system towards the equilibrium or the rest side. And these problems arises as a result of this nonlinearity, which is absolutely you see the nonlinearity dependence of these pneumatic forces of the motion with the mechanical systems. And the strong nonlinearity which is being added to the motion whenever it impacts with the transient features. So, we know that you see the self-excited vibrations can immediately not only cause you see the oscillation or you see the exciting features, but also it can directly affect the system's stability. So, machining and measuring operations are invariably accompanied by these vibrations, and to achieve the higher accuracy in the machining or any measuring part and even the productivity, these vibrations have to controlled, otherwise we can have a different geometric deviations during the process. And for analysis of the dynamic behavior of machine tool rigidity and the stability needs to be checked thoroughly, because these are the two important characteristics for analysis of the dynamic behavior. And when we are simply see that you see the system is not stable or they are providing more kind of you see the excitation, then the straight way it is affecting the rigidity and the stability feature of the entire system itself. And in the machine tool, just like you see in the previous part we discussed, the machine tool vibrations can be divided into three basic features. As you see the spindle motion is of always at the higher speed, maybe up to 20,000 30,000 rpm. And so, they are contributing the huge amount of vibrations into the machine. We can broadly classify this vibration into three basic types: the forced vibration, the self-excited vibrations, and the transient vibrations. And the self-excited vibrations can also termed as the machine tool chatter. So, chatter is also coming under the self-excited vibration, which is simply induced and is being maintained also by the forces which are being generated during the cutting operations. And this you see the chatter vibration is straightway affecting the surface finish, even because we just want the surface finish of the microns level, and which can be only achieved when you can control this chatter vibration. So, not only it is affecting the surface features, but also there is a clear effect of this chatter vibration on tool life, production rate, and even it is producing the huge amount of noise that the worker who is continuously working on that having a significant effect on their nerves, on their like the regular activities, and even in their behavior, because the sound waves are straightway affecting with this. So, the chatter resistance of the machine tool is usually characterized by a maximum stable. Again, you see in that we are simply looking towards the depth of cut, that how much depth of cut is there, accordingly the chatter resistance can be come out, or it can be simply we can say the chatter vibrations are. And the machine tool chatter is essentially a big problem of the dynamic stability for this machining feature. So, machine tool under the vibration free cutting condition can be termed as the dynamical system of steady state motion, because in this case we can at least remove the transient feature of that. And the system of this kind in which the steady state motions are there, we can say that it can be immediately go to the dynamic unstable when the self excited vibration or the chatter vibrations are just increasing with the amplitude, when there is a diverging effect of that, and it can be break into the oscillation around the transient, and we need to brought down this towards the steady state. So, in the self excited vibration, an alternative force that sustains the motion is created or controlled by the motion itself, and when the motion stops, the alternate source which is being generated to control this oscillation is immediately disappeared. So, in the forced vibration, the sustaining we can say alternative force which is being existed independent of the motion and also can persist when vibrating motion is stopped, having a significant feature for controlling the self excited vibration. And the vibration behavior of machine tool can also be improved by reduction of the intensity of the source of vibration, by enhancing the effective static stiffness and damping together. So, now you see here we need to check it out the two system parameters, because we know that the self excited vibration is the system's inherent property. So, how we can redesign the system parameter, especially from the damper side and the stiffness side, so that we can reduce the intensity of the source vibration and we can improve the machine tool feature. And by appropriate choice of the cutting regimes, the tool design and workpiece can be appropriately designed. So, that is you see one of the significant feature of the self excited vibration is an abatement of the sources is important mainly for the forced vibration conditions, and the stiffness and dampings are one of the two important features not only in the forced but also in the chatter or the self excited vibrations. And both the parameters, the stiffness and the damping, are important you see here just to brought down the vibration reduction. And importantly, when we are talking about the stiffness, it is one of the critical parameter for accuracy of machine tool, because through stiffness we can reduce the structural deformation during the cutting forces, and damping is also the crucial for reducing or decaying the transient feature of acceleration, and once you do that, the transient feature of the vibration can be suppressed out. So, how these two parameters are acted, it can be immediately sensed out that the like if we have the damping, then certainly you see the acceleration, the transient feature can be decayed, and if we have the stiffness, the structural deformation during the cutting operations or the cutting forces can be brought down. So, self-excited vibrations can be characterized by the presence of a mechanism whereby a system will vibrate at its own natural, or we can say inherent, or we can say the critical frequencies, which is essentially independent of the frequency of any external stimulus. So, you see here when we are trying to understand the physical significance of self-excited vibration, we need to first characterize the physical system. We need to check it out that what are like the inherent parts or the main components are there through which these vibrations can be generated, and then we need to design the spring or the damper in such a way that we can suppress these vibrations at its own level. So, when we are trying to term this in mathematical terms, the motion is described by unstable homogeneous solution to the homogeneous equation of motion is something coming under the self-excited vibration. And in the contradiction, in case of forced or the resonant vibrations, the frequency of isolation is depending on the frequency of forcing function, which is being externally applied. Like you see, we know that the shaft rotational speed is one of the important feature, and whatever the exciting frequencies are there, when they are just like brought down, the particular integral solution of the equations is showing the forced vibration solution. So, in mathematical terms, we can say that the forced vibration is the particular solution to the non-homogeneous equation of motion, but here the motion is described by unstable homogeneous solution to homogeneous equation of motion. So, here there is a clear bifurcation in terms of the solving method. One is a particular solution to non-homogeneous equation of motion, and one is the unstable homogeneous solution to homogeneous equation of motion. So, you see here the equation of motion is here in the self-excited vibration is homogeneous, but the solution is unstable homogeneous solution. So, self-excited vibration pervade all areas of design. It is not a very specific thing, it is just you see spread it out in that all areas of design and operations of physical system where the motion or time variant parameters are absolutely involved. How? We can see various examples like the aeromechanical systems where the flutter or aerocraft you see like the flight dynamics are there. The aerodynamics straightway even in which you see the separation, the stall, musical or any kind of you see the wind diffuser or even the inlet chugging operations are there. These are all you see the aerodynamic forces which are being generated and they are inducing the vibrations. Even the aerodynamic part, the fluid or the flame instability, the combustion screech, and even in the mechanical system as we discussed, the machine tool chatter, even the feedback networks where the sun damping is being applied there, the pneumatic, hydraulic or any electromechanical servo mechanism. These are all the variety of we can say the applications where the self-excited vibrations are coming due to its inherent nature. And this is being analyzed by Ehrich in its own paper in a very significant way. So, if we want to understand the basic mechanism of self-excited vibrations, the mechanism just shows that in rotating machinery there are various categorizations of the self-excited vibrations are like the whirling or wrapping, the hysteresis whirl, or even the fluid which is being trapped in the rotor and creating the self-excited vibrations, even the dry friction whip, fluid bearing whip, and even the seal or any blade tip clearance effect. Because when the clearance is there, though you see we know that the clearance is being provided just to flow of the fluid or even for any thermal expansion during the operation, but this clearance is also creating some kind of self-excited vibration not only in the bearings, not only in the gears, but also in various components of the turbo machinery. Even we know that the propeller or the turbo machinery whirl during the whirl action. One of the important parameters which is being analyzed in the self-excited vibrations are the parametric instabilities. Because sometimes when we define the parameter according to the critical design of the system, we know that the parameters are always under the dynamic action. When they are crossing their range, they are exciting the system in a huge way. Even asymmetric shafting, the pulsating torque can produce this, or even we can say that the stick slip rubs or chatter. These all factors, we can say that these factors are coming under the category of self-excited vibrations, and these vibrations are nothing but the oscillation that are excited by the motion of the system and being we can say transmitted fastly due to the inherent nature of the system is. Like we can see the example here, the self-excited oscillations are induced by the nonlinear forms of damping, where the damping term is a negative or certain range of motion. And when these mechanical systems that exhibit the negative damping, it clearly shows that the self-excited vibrations are there and even the system instabilities are there, because we know that the damping positive means whatever the function which is being defined for the damping, it has to execute that. But instead of the dissipation of the energy, if the energy is being supplied to the system by the damping, can be termed as the negative damping. And when such things are happening, means when the energy is being supplied by one of the important parameter, then it makes the system unstable. So you can see that the example means we have a moving belt, and over which you see the we can say that we have the mass, and because of this velocity of the moving belt, there is instead of having the vibration suppression of the mass, the energy is being supplied by the damping material of the belt to the mass. So here we can say that the system will certainly make an unstable effort because of this negative damping, and this is one of the universal criteria that whenever you, and that is why you see we can say whenever we are designing the damping, we need to find out that it should not be over damped system, so that the energy is being supplied due to high viscosity to the system, and this makes the system unstable. And the instability of rotating shaft, or the flutter of the turbine blades, or the flow induced vibration in the pipes, or in we can say automatic wheel shimmery, they are all a typical example of self-excited vibrations, because in these cases the system can go up to the instability features because of these energy supplied towards the system, because we know that if the energy is minimum of the system is stable, but here we have a different kind of system setup. So a system is dynamically stable. Now we can categorize even if the motion, displacement or anything converges or even remains steady with the time. But if the amplitude of the displacement increases, or we are saying that if the diverging effect is there of the amplitude or even the system energy, with the time the system is dynamically unstable. And when this energy is being supplied, certainly there is an exciting feature and the energy is coming for further excitation. How we can make the system stable? So the motion which is diverges and the system becomes unstable, the energy is directly faded into the system, as we discussed. And that is why you see here the self-excited vibration is always creating some kind of instability in the system itself. So let us talk about the mass spring damper system. As you can see on your screen, in that the force balance equation is this according to the Newton's law, and we discussed already these things. So we have now the equation of motion mx double dot plus cx dot plus kx equals to 0. And now if we are substituting the basic displacement as the input feature, x of t equals to a e to the power lambda t, when we are keeping all the things, we know that the characteristic roots of the equation, this is characteristic equation, is just giving you the eigen values of that, or in other term we can say that these are nothing but our natural frequency. And since the solution which is assumed to be x of t, which is because it is a harmonic part, so c into e to the power lambda t, the motion will be diverging and showing the aperiodic nature only when the roots are real and positive. And how the roots could be positive? You can see that the lambda 1 comma 2 are nothing but minus c by 2m plus minus square root of c square by m square plus minus 4k by m. When the roots are real and positive, when you have the damping negative, and when the damping is negative, minus c by 2m will show the positive feature. That means you see here, from somewhere, means from the damping or any other feature, the energy is being fed by the self-excited vibration to the system, and that makes the system diverging feature or unstable or the aperiodic part. This situation can be immediately avoided if the c by m and k by m are positive, and we can say the motion will be diverging if the roots are of complex conjugate with the real parts as well. So what I mean to say that we need to check it out that these things means we are saying that the positive damping, positive stiffness, and that is what these features are. When they are acting with their own properties to absorb the energy or to suppress the entire oscillation, we can say that we can brought down the system towards the stable feature or equilibrium feature, and you see whatever the solution features are being coming out, it is absolutely under steady state phenomena. So thus the fundamental criteria of the stability in the linear system is the roots of characteristic equation should have the negative real parts, so that we can produce the decaying amplitude. Because we know that when we are just trying to draw this with the damping effect, we have oscillatory decaying exponential feature and the sinusoidal features are there, and that is only possible when you have the real roots negative. The whirling speed at the beginning of onset of stability is the shaft natural or the critical frequency, irrespective of whatever the speeds are. So the direction of the whirl in this whirling speed may be of the same as the rotational directions of the shaft rotations are, or we can say it may be opposite to the direction of shaft rotation when you have the backward whirl. So the forward whirl and backward whirl are absolutely depending on the direction of destabilizing force in the whirl action of the shaft. So this is what you see, the fundamental criteria which we can simply see in this diagram. You can see that we have the vibration amplitude 1, in which you see there is a clear decaying of vibration is showing the stability features in that, because we have the real parts in the negative way of any complex roots. But while in the other end you see that there is a clear diverging or aperiodic effect is coming, because we have the real parts are positive of the complex roots and they are showing the negative either c by m or k by m with the energy fed to the system, which makes the system unstable. So we can have, you see, the examples of that. Say the mass is supported by the spring is carried out by the moving belt through the friction, and this friction coefficient, which is absolutely in between the mass and the belt interfacing, is a function of relative velocity with respect to mass and the belt. So you can see that the friction coefficient and the relative velocity, you can find simply the gradient, and then you can see that initially when the velocity is low, the friction coefficient is just going down, and after a certain time it is now increasing. So when the friction coefficients are increasing, it produces the heat. You can make the equations there itself, like mx double dot plus kx, these are the two inertia force and restoring forces, which makes an equal to the friction forces mu into mg, whatever the gravitational or the weight is there of that. And even we can add the other features of the movement of the belt with the masses, like plus alpha, which is nothing but the coefficient absolutely based on the material property, into x dot minus v0 mg, or else even we can say that it is equals to minus mu 1 plus av0 mg plus mu times of alpha mg x dot. So in all we can say that what we have two main things. One, the frictional coefficient, and one is alpha. The frictional coefficient, the alpha is nothing but equals to your damping which is coming out due to the material property of your belt. So when we are trying to resolve these things, we have the inertia forces which are being balanced by the restoring force, the frictional force and the damping forces which is mainly due to that. And here the damping which is nothing but equals to the, which is always you see like coming along with the frictional coefficient is nothing but equal to the mu 0 alpha mg into velocity, and this alpha is nothing but the negative damping which simply causing the diverging figure or unstable figure in the vibrations. So as the vibration goes beyond certain level, means when you see it is increasing, the velocity and even the relative velocity x dot minus v0 will increases, and this cause the friction coefficient to decrease and then vibration decreases. This cycle of increasing and decreasing vibration repeats itself forever, and the moving belt can sustain vibration is always having a self-excited vibrations are. So this is one of the significant criteria there. If you are going towards another example, we have a solid oscillating in the fluid and can interact with the fluid and can produce the intersecting behavior with that. We can see the relative aerofoil motion against the oscillating solid body's motion, and we can say that the velocity vector can be simply brought down there itself. So we have a clear drag forces, the velocity is moving, and you see here the mass which is being like oscillating at that point, and thus the lift and drag forces are being absolutely acted on this solid. Now you see, you can see on the diagram there are, you see the spring and the dampener is being attached to there, and the velocity vector is just going into that direction. Now if you are considering the long cylinder length, say L, which is being supported by the spring on one end and damper on other end, and the total like we can say the diameter of this solid is d, then we can simply find out that how these forces are being surrounded on that. So the equation of motion is as simple, because we have three main components: the mass with the inertia force, the damping C with the damping force, and stiffness with the restoring force, and then it is equals to what are the forces which are being coming due to the velocity v are termed as the lift forces. So f of t is nothing but equals to half rho v square dl c1, where you see the rho is the density, v is the velocity is coming, and all other features are with the dimensional details. So the term which is varying with the force, whatever the lift force f of t is, now you can see that this is like the Kerman vorticities are there, and they are absolutely moving at certain Reynolds number. So you can see on the solid these forces, the vertex motions are there, and the forces are being generated all along the circumferences of these ball. So due to the vibration of the cylinder, the solid feature, the lift coefficient is no longer constant, certainly, because the shading of the vertices. And when we are saying that the CL is not a constant figure, it is being like the pulsating feature, we have CL is nothing but equals to some constant into sine of omega t. And you see this C10 or whatever the coefficient is absolutely depending on what is the shape of the solid is. And we can say omega, which is nothing but the exciting frequency, is nothing but equals to 2 pi k, the stiffness of that, into whatever the displacement divided by d, where k is nothing but equals to the Storal number, and we can say the Reynolds number which is being there as the ratio of inertia force and damping force, we can simply brought down up to say 1000 for a laminar flow, and k can be simply brought for this case when you have the laminar flow is 0.21. So we can simply say that the velocity v is nothing but equals to d by 2 pi k square root of omega this k by m, which is nothing but the natural frequency, or else we can say that the velocity is nothing but the natural frequency into d divided by 2 pi k. So the cylinder which is vibrating can also becomes vibrate in the violent feature or in the resonant condition in the flow when you have the clear exciting frequencies, the forcing frequency by V and the natural frequencies are coinciding. And when the flow velocity becomes even higher than this, then the flow becomes turbulent in this case, and the lift flow, whatever the lift is coming down, whatever the lift is coming to the system is being in the random part. And this randomness, because of you see the turbulent flow of the air, and which is causing you see the entire random vibration in that, is coming under the flutter feature in this, and flutter is a perfect phenomena of the self-excited vibration. So you can see that this is what you see, a rigid wing which is attached to that. In the another feature we have a clear velocity V, when it is attached to this, there are you see this absolutely attack, the rigid wing attack is there to a rigid support, and the springs are being there just to support that the vertical motion. So we can write even for this equation, you see we have a straight way, the spring which is being hanged out on the wall, and it is being control that entire thing. When you see the velocity, the air velocity is dragged into that, there is a clear inclination motion, and we can have the equation of motion mx double dot plus kx equals to minus L cos alpha minus D sin alpha according to the resolution of these two components. And we can write the equations in that, you see L equals to rho by 2 V square plus x square, or we can say that it is nothing but equals to rho by 2 V square plus x square LC rho c by rho theta, and D which is nothing but you see the energy formations in the Laplacian transformation, and this D is equals to rho by 2 V square plus x square into LC rho CD by rho theta, where you see we can say that the theta which is you see the balanced angle is theta 0 minus alpha, or alpha is nothing but equals to tan inverse of velocity x dot divided by V. So when we are plotting these down, we can simply get the equation of motion mx double dot plus rho by 2 this VLC dc1 by d theta and all, and we can say that finally the equation, the balanced equation for these the aerofoil motion which is even being hanged with the say spring controlled is nothing but equals to mx double dot equals to rho V square LC by 2 dc1 by d theta theta 0, where we have a clear interaction of the inertia forces along with whatever the air motions are. So when we are doing these things, we can say that there is a clear torsional feature of the vibration when the center of gravity and aerodynamic centers are being even coinciding, and when such things are happening, we can simply get the equation of motion with me square and this I, this is nothing but equals to the inertia force, the moment of inertia, mass moment of inertia, and we have me omega square, plus you see whatever the stiffness features are being coming as k minus rho V square LC by 2 dc1 by d theta, and also you see here we can simply brought down the entire you see the dynamic features with the static diverging speed V diverging is nothing but equals to the square root of 2k divided by the rho LC dc1 by d theta or dcm by d theta. So when we are jotting down these things, we know that the symmetric profile of the aerofoil with this diverging velocity will be absolutely depending on the k and also with the dcl by d theta. So when we have the diverging velocity high, the speed capacity will be more of the aircraft, and then it becomes the system is more diverging and it becomes the system unstable. So here we can simply say that even if we want the stable aerofoil motion, we can simply choose these system parameters with the k, rho and you see the dc1 in such a way that we can brought down the self-excited vibration, which is simply showing the flutter vibrations of the aerofoil motions. So in this lecture, we mainly discussed about the vibration generation due to self-excited vibration, And this self-excited vibration, though it looks like that pretty simple, that you see, like because of the inherent nature of the system or some system parameter, the parametric excitations are there, but it contributes even up to the instability of the system by feeding some kind of energy to the system. So when we are designing those things, we need to calculate the self-excited vibration, because this is something, you see, the non-homogeneous solution, and we need to just brought down to the homogeneous solution of the equations, and it is absolutely different than the forced vibrations in terms of the solution itself. So in the next class, we are going to discuss about the vibration generation mechanism, but the flow induced. That when you see even the fluid interaction is there, the fluid, as we discussed already, the various mechanism of the fluid induced vibration FIV. Here also now we need to check it out. We need to computationally check it out, rather, that how you see when the fluid is just moving towards that how the mechanism is working towards the vibration generation, and we will certainly take various examples to understand the physical significance of such vibrations are. Thank you.